everybody. I am Dr. Ducey with the Missouri Western State University Department of Chemistry, and this is our chemical demonstration show as we wrap up the Chemists Celebrate Earth Week week. So it's Gold Fridays here on the Missouri Western campus, so we have a little bit of time to be able to do some demonstrations today, and we're going to try and relate our demonstrations to the Earth Week theme from the Chemists Celebrate Earth Week. So CCEW has identified reduce, reuse, recycle as our theme. And so what we're going to be doing is talking about what carbon dioxide is. We'll look a little bit about its properties and sort of some of the things that we're concerned about as we think about carbon dioxide. So I see Dr. Clapp is on his way in here. So we'll introduce him here in just a moment as well. So what I'm going to do is let's go ahead and take a look at some carbon dioxide and properties of carbon dioxide. Are you able to see, or do you have a Facebook feed pulled up there?
I'm trying to.
Okay. We're going to see if we can see you guys out there, and hopefully you can see us as well. So, all right, so while we're doing that, let me get some stuff set up. I had our amazing stockroom person, Victoria Sample, pick up some dry ice for us this morning. And of course, dry ice is solid carbon dioxide. So carbon dioxide is kind of interesting. So here's some dry ice. Carbon dioxide is kind of interesting because at atmospheric pressure, under atmospheric pressure conditions, it undergoes something called sublimation. So it goes straight from the solid phase into the gas phase. It is possible, in fact, to create liquid carbon dioxide as well, but it takes some higher pressures in order to accomplish that. Carbon dioxide is also really kind of cool because under very high pressure conditions, it will become what's called a supercritical fluid, which is a fluid that has properties both of a liquid and of a gas. So really kind of a weird form, a weird phase of matter. But supercritical carbon dioxide, we actually use a lot in chemistry, especially when we're doing things like extractions. So I'm going to take some of this carbon dioxide and I'm going to put it here into our big bowl. And we're going to allow that carbon dioxide to undergo some sublimation inside of our bowl. One of the things also about carbon dioxide is that it is denser than air. And so what's going to happen here as the carbon dioxide sublimes is that it's going to force the air out of this container and basically be filled with carbon dioxide. So we can do a couple things to demonstrate that that it's filled with CO2. One of the things that I'm going to attempt to do here, I shouldn't do these things live, but here we go. I'm going to try and put some bubbles into that container. So if I can carefully blow them, we'll see them land over there in that container. So here we go. Oh, goodness, right? So my kids are old now, so I'm not so good at blowing bubbles anymore. Let's see if we can get some in there. Well, I got some bubbles, but they didn't make it all the way there. Well, now I overshot it. Here we go. Well, we made it in, but, okay, 1 second. I've made a mess on the countertop here. Let's try again. Let's see if we can get some better bubbles. Yeah, it's in there. Okay, so We clearly need to have some more CO2 in there though, because that bubble made it all the way down to the bottom. So our container isn't filled with carbon dioxide yet. You guys should probably be able to see in the picture, Dr. Clapp is here with us. So Dr. Clapp has been around the department for a lot of years, been associated with our department at Missouri Western State University as well. And Dr. Clapp is also very active in our local section of the American Chemical Society, the Kansas City section. So, all right, let's see.
And after Earth Day yesterday, this is like follow-up on
That's right, yeah. Let's check and see like how deep the carbon dioxide levels are. So what I'm going to do that, of course, carbon dioxide won't support combustion. And so I'm going to take a candle here, and we're going to light our candle. See if I can light the candle better than I can blow bubbles. All right, and I'm going to dip this candle down into our container, and we're going to see where it snuffs out. Okay, so we're about right here in terms of where we're filled up with our carbon dioxide. So let's put a little bit more in there. Now one thing, so you can of course buy dry ice at the grocery store, at most grocery stores, but you want to be very careful when you use it because it's extremely cold. And so I'm wearing gloves to protect my fingers because I don't want to end up with any frostbite on my fingers. Another piece out of there. That's it. Yeah, that should really should have smashed it up a little bit better so that we filled it up more quickly. Let's try again. Let's see where we're at. Light the candle again. All right, I bet we're pretty much at the top at this point. Yep. Okay. Now let's see if I can blow some bubbles in there. So again, like I said, just kind of fill it up with CO2, displacing the air in there. So let's see if I can, put a bubble in. It was a good sized bubble, but. Oh, goodness. This is always the hardest part. There we go, there we go.
Oh, look at that.
There we go.
We got one in there.
Yes, we do. Look at it.
Ooh.
All right, I'm going to stop there.
Success.
We won't tempt fate again. So, all right. So you saw the bubble in there. Now, of course, it was suspended on the in there. It stayed put because the air that I was blowing in there was only a little bit of carbon dioxide. When we exhale, it's not 100% carbon dioxide. Oops, knocking my glasses off. My breath is not as dense as the carbon dioxide in our container. All right, so we're going to do a couple other things here related to CO2. So really kind of the next thing that I want to do as we tie this to the theme for Earth Week, where does carbon dioxide come from? That's going to be one of the questions that we have. And of course, carbon dioxide comes from lots of things, but in terms of how we contribute to carbon dioxide in our atmosphere, a lot of that is through combustion, right? So we burn things, and burning a lot of different things. It could be coal, it could be liquid fuels, wood, right? Lots of things. So I'm going to do a little demonstration here. This is kind of a fun one. Where we're going to demonstrate some combustion. Oops, here we go. And of course, I forgot my. That's okay. Here we go. All right. So we're going to do some examples of combustion, and I'm going to put a little bit of ethanol into this small bottle that I have here. And then what we're going to do is we're going to ignite that ethanol. Now, of course, ethanol, which we get primarily from fermentation, right? So if we take and we burn ethanol, so I put a little bit on there so you can see it. right? Of course, it catches on fire, it's combustible. We use ethanol for lots of different stuff, but certainly combustion is one of the things that we do use it for. We use it as a fuel additive in particular, when we have ethanol added to our gasoline to power our cars. So we can see some ethanol burning there. The ethanol burning, it burns pretty slow. It's not a terribly hot flame as flames go. And so what I've done with this little bottle is we're going to speed it up. So I'm going to have Dr. Clapp is going to do the honors here of igniting this. So, sorry to go out of frame on you there, but I dumped out that ethanol liquid that was in that bottle because I'm not really interested in the liquid. So we're going to have Dr. Clapp, he's going to light it. Okay, there you go. So you saw a little pop, right? So that little pop was the ignition of the vapor that was, the ethanol vapor that was in this bottle. Now, of course, when we power our vehicles, we use that expansion of the gas, that quick expansion to power our cars. But one of the things that happened when we did that, right, when we burned ethanol, we get carbon dioxide and water as the results of that combustion reaction. Now, we could stop there, but I mean, this is chemistry demonstration stuff, so we're going to have a little bit of fun with this while we go, okay? So we call this edutainment at this point, right? So you already got educated, now we're just playing. So I'm going to put a little bit more ethanol, but we're going to go to a bigger bottle this time. So I had a little bit larger one there.
What do you think's going to happen this time?
Yeah.
More ethanol.
So I like this demonstration though, as we think about like how your car is powered, because this is about the size of a cylinder on maybe a 4-cylinder or a 6-cylinder engine. It's about that volume. And so if you think about the gas expanding in that volume and then pushing that piston up, that's the kind of power that we're using. There we go. Right, so you saw a lot more. Of course, we should have seen a little bit more out of that because there was a bigger bottle. Let's go ahead and continue to scale this up just a little bit.
Are we going to go bigger, Mike?
Yeah, we're going to go bigger. Yeah, go big or go home. That's what we say, right?
Right.
So let's see. Okay.
So you know that electricity is generated typically through coal or oil or some sort of petroleum product. And so every time we turn on a light, we're creating CO2 because what powers the system is the combustion of something. And that's why we always turn the lights off when we're done and turn things off when we're done when we leave a room. So let's see what this next one does.
So we're a little bit bigger here. There we go. So now, as we play here, right, as Dr. Clapp was just talking about, when we turn on our lights, right, we may be using a fossil fuel in order to generate the electricity that we use to run those lights. Where we're at right here in St. Joseph, Missouri, the region around us has actually is using a lot of wind power now. We have some very large wind farms located just to the north of us in the King City area. And so, of course, that's one of the ways that we can reduce our dependence on fossil fuel is to use some of those renewable sources. So we're going to go a little bit bigger here. So this one is a little bit different because it has has some screws in it. And so we're going to use this one to kind of demonstrate how that combustion engine works. So of course in a car's engine, what we have is a spark plug, right? And the spark plug is what generates the energy to ignite the fuel that we put into the cylinder. So I'm gonna add some electricity to this. Hopefully this does not mess with my with our feed a little bit. So I have what's called a Tesla coil. So this is basically going to give us a spark to drop into our little tube here. So I'm going to go ahead and we're going to put this in. Here we go. There we go.
That is cool.
That was good. Yep. That was good.
Nice job.
All right.
Thank you, Nicholas Tesla.
That's right. Let's see, we have just a couple more that we're going to do, and then we're going to look at the properties of carbon dioxide when they dissolve into water, because that's going to be one of the concerns that we have about increasing carbon dioxide levels in our atmosphere, is that they actually affect a lot more than just the atmosphere. So we talked about global warming, but the effects of carbon dioxide can be felt also in our oceans, for example. All right, so we'll do this big one here. Okay, I'll make sure that all of the ethanol is out. All right, so will Dr. Clapp do this one? There we go. Just turn the bottom there. Turn it up till you hear it buzz. Okay, here we go. This is a little bit bigger. Woo! Yeah. All right. So now one of the things that I want to show you, I told you earlier that, of course, that if we burn that ethanol, that we get water and carbon dioxide. And so one of the ways, and we also said earlier that carbon dioxide doesn't support combustion. So one of the things I want to do here is I'm going to put a little bit of ethanol back into this, and we're going to try and do it again. Okay, so okay. And we're going to see that we really don't get much. Yeah, see? We can't ignite it again. The reason we can't ignite it again is that it's filled with carbon dioxide. I didn't allow the carbon dioxide to come out of my bottle here. So that gives us some evidence that, in fact, we filled this up with carbon dioxide when we did that reaction. Okay, so let's go on to some other pieces here. So one of the things that I wanted to show you was the effect of dissolved carbon dioxide on some water. Now what I have here is a really dilute solution of hydrochloric acid. It's about 0.1 molar for my chemist folks out there. And what we're going to do is, so it's red, by the way, I should share that because I put some universal indicator in there. That's important to know. So what we're going to do is I've got a saturated solution of sodium carbonate right here. Sodium carbonate is related to carbon dioxide through some equilibrium processes. What I'm going to do is, well, and sodium carbonate, by the way, is basic. The hydrochloric acid, of course, is acidic. Now, one of the things you might wonder is, like, how do I know it's basic? Well, if you've ever put some sodium carbonate on your fingers, it feels slippery. Those slippery things, they tend to be bases. That's a pretty good clue that it's a base. So what we're going to do is I'm going to take this saturated sodium carbonate, and it's saturated on purpose because I wanted it to have a really high density so that when we put it into this container, that it goes straight down to the bottom. Okay? So now you really can't tell that it's gone down to the bottom because I didn't put much in there. But what we're going to do is we're going to start to see some color changes occur inside of my cylinder. We want to be real careful not to mix it too much because we want that sodium carbonate to stay down at the bottom and start to make those color changes. So we're going to do this. Now I will tell you that normally this is an experiment or a demonstration that Dr. Lorimer in our department does, and he does it very, very well. So we're hoping that I can do it reasonably well for you to see. Okay, so far, not much, right? Okay, let's add a little bit more here. We're going to go and put quite a bit in. Okay, and I'm going to do it really slowly so that we try not to All right, so now what we're going to do, let that develop here for just a second.
You can even see the bubbles forming.
Yep. So you can start to see the color change associated with the universal indicator. Gosh, I hope you guys can see that in our YouTube, or sorry, our Facebook live feed. So you can see the dark color down here at the bottom, and that is sort of a bluish color, and then our yellow, we'll see a little bit of orange in here, and then red. So this is where it is basic, because sodium carbonate is basic. And then it gets increasingly acidic as we move away from that very dense area of sodium carbonate up into our hydrochloric acid layer. Let's see if I can do it a little bit more. I'll put a little bit more in there so that we can see if we can get that to develop a little bit more. Oh, I think I mixed it a little bit. Oh, no, that's not too bad. That's not too bad. Okay.
You can see kind of go from blue to green to yellow to orange and then into the red.
So the point of this is that that sodium carbonate changes the pH of our solution, and carbon dioxide, when it dissolves in water, can do the same thing. And so we're going to look at that here in our next demonstration. So I'll leave this over here, and we'll kind of watch it. It may mix a little bit because you can see we're generating some bubbles as the hydrochloric acid mixes with the sodium carbonate to generate carbon dioxide. So here we go for kind of our last big example. How are we doing on time? I said about half hour. That's right. That's what we're going to be. All right, so what I have in here right now is some water and universal indicator. So you see that it's kind of a blue-green color, which is exactly what we would expect. The water should be pretty close to neutral at this point. Now what I'm going to do is I'm going to add some sodium hydroxide to this. So I'm going to intentionally make this basic. Now when we do this, we're going to see the color change, and it'll become a very dark blue-purple when we add it. So I'm going to allow that to mix here for just a second so that you can see that nice blue-purple color. So you can see, oops, I got a little spill there. All right, so now I don't know if you can tell, but it's starting to turn a nice purple color all the way through, because that little bit of sodium hydroxide that I added has made it basic. So the thing that we're going to do next is we're going to add some carbon dioxide to this. So I'm going to put a piece of dry ice in here. And the reason we're going to put some dry ice in here is I want you to see what happens when carbon dioxide dissolves into water. Because again, this is one of the concerns that we have with increasing carbon dioxide concentrations in our atmosphere, is that more of it dissolves into the water, and when it does, we're going to get effects like we see here. So I'm going to take a small piece of dry ice, and we're going to drop it in there. We're going to let it bubble. So yeah, this is entertaining too. Right here's your edutainment. But watch the colors, okay? Watch the colors in here. So that's the piece that we're interested in, is what effect does that dissolved carbon dioxide have on our solution pH. So this will take just a few minutes here to develop. Now, why is this important? Why is the pH of the water important? It's really important if, say, you're a piece of coral or a fish or a mollusk or something like that, where you function at a particular pH. And so if that pH gets changed, sometimes even just a little bit, it can be really detrimental to your life cycle. So we want to make sure that we're not allowing oceans and other bodies of water to undergo these drastic changes in pH. So some of the effects of dissolved carbon dioxide we're already starting to see in some of the more vulnerable and delicate biological systems, such as coral reefs they tend to be very, very sensitive to changes in ocean pH.
So it's also considered a greenhouse gas. Dr. Ducey didn't say that earlier. As a greenhouse gas, it actually interferes with the re-radiation of sunlight and other materials trying to leave the earth after the sunshine gets through the clouds into the earth's surface. And that re-radiation gets trapped by CO2, which helps form more clouds and warms the planet. And as a result, we're trying to limit some of our CO2, which we talk about as our carbon footprint. And that's very important that we do that, because it only takes a few degree temperature changes, and then we see things like polar ice caps melting and raising of sea levels, and all the things we have been seeing in the last 50 years or so are actually starting to happen.
Okay, so I know that it doesn't seem like much has changed here, but actually we are starting to see the change. I can see the purple color is now beginning to be a little bit lighter. And what happens when that carbon dioxide dissolves into the water is we form something called carbonic acid. And that carbonic acid is going to neutralize some of the sodium hydroxide. In fact, over time here, it's going to neutralize all of the sodium hydroxide. Yeah, so now if you look down here at the bottom, I don't know how well you can see that, but it's starting to turn blue down here. In fact, it's almost starting to turn green down near the bottom.
Kind of see the green. If the lighting's right, you can actually see the green sort of coming up with the bubbles, and it's no longer that.
There we go. So now it's really starting to turn. So we've gone from from acidic, so a pH probably around 12, to right now a pH of around 7. So with that that pretty green color there.
As we get more and more acidic, the numbers go down. So if you remember basic chemistry is the low pH is acidic. So when we talk about acid rain, we're talking about low pH, numbers that are like less than 7. The 7's neutral.
Okay, so now you can start to see the yellowing of this. So again, right, if we go back to what we made earlier, sort of our rainbow effect here, right? This was a basic, and then we became more acidic as we moved towards that red color. And so the yellow is right next to the red. So the yellow color is really pH around between 5 and 6 for a universal indicator.
So most of our seabeds are made of carbonates. Limestone, in essence, is carbonates. And so as you change things in nature, as you're changing, if you acidify them or if you make them more soluble in the ocean, what ends up happening is we get more and more CO2. More and more CO2 is released into the ocean. And as the temperature rises, we kick out, because gases are less soluble as temperature rises. The CO2 is released into the atmosphere, and it compounds that greenhouse effect. And the seabed itself is a tremendous source of carbonate. So we have to be very careful about what we're dumping into the oceans. And that's why we manage the pH of all things, whether we're dumping them in the river, or whether we're dumping them in the sewer, or whether we dump them overboard.
Okay, so we're getting, again, to pH around 6 or so. If we let this go long enough, it will get orange in color. It doesn't go all the way to red, but it definitely, we've changed the acidity or the pH of this solution significantly by dissolving our carbon dioxide into it. So I think that's what I have.
I think that concludes our CCEW sort of experiments. When hope you had some enjoyment and picked up a little science. I'm going to be rebroadcasting this on the ACS website, which is acs-kc.com. After I convert it to an MP4, and we'll upload it on there so you can watch our entertaining carbon dioxide footprint video.
All right. Certainly, if you have any questions about any of the things that we did today, send them to us, and we'll get back to you with an answer.
Yeah, thank you.
All right. Bye, everybody.